So I'm going to start chapter 3 today with substances and solutions. Chapter 3 is, we'll be talking in this chapter with formula mass and the mole concept. We're going to also determine empirical and molecular formulas. If you remember in chapter 2, we were talking about the empirical and molecular formula in a qualitative way, but here we are going to determine the empirical and molecular formula in a quantitative way. How we can able to determine using numerical values, percentage values, or grams. That's what chapter 3 is about. We will be also discussing about concentrations of solutions, which is molarity of solutions, and also other units of solution concentration. It will be discussed or covered in this chapter. Chapter 3 is basically, I call it as a quantitative type of chemistry. We're doing more of quantitative numerical values rather than the qualitative types. Again, it's very important that you need to have a periodic table with you in order to following the slides, the explanations, and the calculations. You must have a periodic table with you. Okay. So the first thing that I'm not going to go over again with covalent compound and ionic compound. Now I guess it's boring for you to say the same thing, covalent and ionic compound. I am assuming that we have like 20 participants are in the Zoom building right now. Each one of you are perfect and know, and you are master of knowing the difference between covalent and ionic compounds. And I'm not going to ask you this question again. But we're going to see their quantitative value here with the covalent compounds. There is a term that we use, a molecular mass versus a formula mass. When you are a molecular mass is right here. A molecular mass is used for calculating a covalent substance. So the formula mass, the formula, I think the writing is wrong here. The formula mass for a covalent substance is referred as molecular mass. Okay, let me put it in a different way. When we are expressing about the quantitative weights for covalent compounds, we're saying molecular mass. Okay, molecular mass is a quantitative value that stands for the weight of covalent compounds. Okay, and on the other hand, we have something called formula mass. Formula mass is corresponding with the weights of ionic compounds. Okay, this is just a terminology. Okay, the idea is the same, the concept is the same. When you are calculating the weights of covalent compound, the term that you used is molecular mass. When you are calculating the weights of ionic compound, the term that you use is formula mass. Okay, now having said that, yeah.
Question, sorry to interrupt.
No problem.
So last class we talked about formula weight and molecular mass as well. Is formula weight the same thing as formula mass?
Exactly.
In this case? Okay, perfect.
Exactly. Yes. Thank you for that correction. Yes. I would use formula weight. That's the same as formula mass. Molecular weight is the same as molecular mass. Yes. Good point. Great. Brittany. Yes. So let me give you an example here. We have let me clear up this a little bit. So if we have aspirin, an aspirin molecule is a covalent compound and has a formula of C9H8O4. All of these are organic compounds, I mean covalent compounds. They are nonmetals, carbon, hydrogen, and oxygen. So these actually refers as a covalent compound right here. Now, when we are talking about the weight, we're talking a molecular mass or a molecular weight. So how do we calculate the molecular weight or the molecular mass in this case? The molecular mass for aspirin is 180.15 mu. The way how we get is, again, we're going to go to the periodic table. We count the number of carbon atoms we have. The quantity of carbon atom is 9, C9. The quantity of hydrogen is 8, that's H8, the subscript. The quantity of oxygen is 4, that's O4. And we multiply by their respective atomic weights. These numbers, like 12.01 or 1.008 or 16, again, they can be found from the periodic table. That you must have that. Unfortunately, you need to have that number with reading your quiz or your assignment, your exam, or if you are following the lecture. So what we need to do is, in this case, we need to multiply 9 by 12.01, which is the atomic weight of carbon, 8 by 1.008, which is the atomic weight of hydrogen. There are 8 atoms of hydrogen. We are calculating the molecular weight for aspirin C9H8O4. And for oxygen, we have 4 atoms of oxygen. We multiply by 16.00. So when we added them up, we get 180.15. Here you get the structural formula for aspirin, the double arrow, the double line, the first double bond. The gray color refers for hydrogen, the black color refers for carbon, the red color refers for oxygen. Shows us the structure of aspirin here, and 180.15 refers as the molecular weight. I can simply use molecular weights. That's how we calculate molecular weight. Okay, now we have also here ionic compound. Now, for ionic compound, we use a formula mass or formula weight. They are the same. Formula mass or formula weight, okay? So, first of all, we know what ionic compounds are. Ionic compounds are, they are composed of a discrete cations and anions, okay? Cations and anions, they are combined in ratios that yield an electrically neutral bulk substance. So a good example of ionic compound is none other than sodium chloride. Okay, so here we use sodium chloride, and we wanted to calculate the weight of the formula weight or the formula mass of sodium chloride. Okay, so we have to count the number of sodium atom, which is 1, the number of chlorine is 1, and we're looking for the average atomic mass from the periodic table. The corresponding atomic mass or average atomic weight is 22.99, that's for sodium. For chlorine is 35.45, and we multiply that by 1 because we have the ratio is, in this case, is 1 to 1. So we multiply that and then we add them up, okay? So we get 58.44 AMU. So this number, 58.44 AMU, is referred as the formula weight of sodium chloride. So it's now clear what's formula weight or what's molecular weight, right? We use formula weight for ionic compound. We use molecular weight for covalent compound. It's nothing new. It's a matter of terminology, the way how we define it. Okay. Then we're going to we have here something called the okay. So let me continue with this. If something will happen, don't go. Now let me continue with this. I hope everything is okay. Now we're going to talk about formula mass and the mole concept. Okay. Now we know what formula weight, we know what molecular weight is. Okay. Now I'm going to introduce you the term called the mole concept. Mole, M-O-L-E. The mole is a counting or amount unit similar to a pair or dozen. Let's say, Brittany, you go to the store, food line, and you buy a dozen of egg, right? How many eggs are you going to buy if you go to the store?
12.
Well, you don't have to count that. It's 12. Dozen always refers to 12. If you buy one case of soda, one case always has pretty much 24, right? That's
Between 12, 18, and 24, because Mountain Dew and Pepsi up the game, Professor. They got a pack of 18 now.
well, okay. Well, I'm old school, so I know 24. So, a case, as far as I know, is 24. But if they change it, it's a market. But always when you're talking about like we call gross. I don't know in US they use gross. Gross, one gross. One gross. Oh, what is this? One gross is always refers to us how many? One gross. Does anybody know one gross equals to? One gross equals to 144. A gross of paper, a gross of pencil in our daily life is 144. Okay. A case, well, if they change it now, it's 24, but I don't know if they change it, but the case always refers to 24. But if that's the confusion, okay, let's go to dozen. A dozen always refers to 12, right? But what these things are we use in our daily life. Okay. In chemistry also, matter is made from atoms or particles or molecules, right? In billion and trillion number of atoms or molecules are there. So that cannot be counted. Okay, it's very hard to count. Even scientists have discovered that a drop of water, just one drop of water, has about like 2 times 10 to the power of 23 molecules of water, one drops. That's experimentally determined or proven. Okay, one drop of water has 2 times 10 to the power of 23 molecules of water. You can imagine how huge it is. So, how we, as a chemistry students here in the Zoom, can able to track those kinds of number. So we have to introduce the concept of mole, right? So just a dozen refers to 12, a gross refers to 144. One mole, a mole contains about this number. 6.022 times 10 to the power of 23. So this number has a special name. It's called the Avogadro's number, Amado Avogadro's. Okay, that is this guy right here, an Italian guy who actually came up with this number. One mole of any substance has 6.022 times 10 to the power of 23. If it is 2 mole, it's going to be twice of this. If it is 3 mole, it continues like that. So how do we know? Say for example, if I have a 58 gram of water, okay, and if I ask you in a 58 grams of water, how many molecules of water I have? That's the question I will ask. Okay, how many molecules of water I have? Can anybody gives me counting of particles or molecules of water in 58 grams of water? Who can try that? Or who can,
Would it be,
I don't want
would
you
it,
to count, but you can give me an idea
would
how,
it be,
how I can able to do that. I'm sorry, did somebody say something?
I said, would it be 58 times Avogadro's number?
Explain it more, Marcus.
Okay, so I'm saying,
Professor, would that be the how we did last class? We did 58 divided by the 18.015, got 3.2 moles, times that by Avogadro's number, and then we just simplified it as 6.022 times 10 to the 23rd.
Okay,
Do you want me to go into more detail as to how I got that
please,
6.022 times
please
10 to the
do.
23rd?
I'm going to create a new slide here. Hold on. We're going to be leading to this, and then I'll create a new slide. And then, okay, we have the question is for everybody. We have 58 grams of water, and we are interested to count the number of molecules. How many molecules, the number of molecules that are present, okay, that are present in 58 grams of water. Okay, go ahead, Brittany. You can lead us to the point.
No, you're fine. So we
Okay, go
have to
ahead.
calculate hydrogen and oxygen. So out of this equation, we have one hydrogen,
Okay, one
which
hydrogen. Okay.
yes, which based off of the periodic table has one mass. Then we have
That's going to be 1.008, I believe, right? Okay.
yes, professor. And then the same for oxygen, which will be
Right.
15.999, I believe.
Okay, but we have two hydrogens, so we have to multiply this by 2, right? Because we have.
Correct. Well, I'm just breaking down the steps first, professor.
Okay.
But you're correct. You're correct. And then you would do the same for oxygen below that. And then you would times that by, what did we multiply it by? Just one for oxygen. Then what you're going to do is you're going to add those two and you're going to get 18.015.
Say one more time.
So for hydrogen, that's going to be equals 2. And then below that, you're going to do oxygen.
Okay.
Times 1. So that's 15.999, I believe.
Yeah. Yeah,
there we go, 8. Okay. And then you're going to times that by 1.
Yes.
So you're going to get 2 on the top and then 16 on the bottom. And we added those and the total was 18.015. Now from there, what you're going to do is take the 58 and divide it by that 18.015, which gives you 3.2 moles of water.
Okay, hold on. What's the number of moles that we have here?
3.2.
3.2. Okay, moles of water. Okay, now I'm going to hold you here. Now, so far, anybody has any question? How Brittany converted 58 grams of water into moles of water? It's very important that I need to know that I want that everybody is on the same page. Okay, so up to this point, we still have to do more work to calculate the number of molecules, not the moles, but Brittany is following the right step. She has to first convert the gram of water into moles of water. And eventually, she's going to convert the moles of water into the molecules of water, right? So, but up to this point, anybody has any question, please, before we go further? I don't see any hands raising. Okay, go ahead. Continue, please, Brittany.
Okay, so from there, you're going to do the 3.2 times Avogadro's number. So it's 3.2 in parentheses times 6.02. Close the parentheses times 10 to the 23rd power.
Right.
So then from there, it equaled out to 19.3 times 10 to 23rd power. And to simplify that, we did 1.93 times 10 to the 24th. You stated you can either increase that power or decrease the power only by 1.
Right. Very good, excellent. So in 58 grams of water, we have 19.3 times 10 to the power of 23 molecules of water, or we have 1.93 times 10 to the power of 24 molecules of water. This simply, we can move the decimal point to the left. When you move the decimal point to the left, then the exponential factor will be increased here. So that's how we determine, because we do not see in our eyes molecules. They cannot see them. They're very, very smaller particles. There's only special kind of instrument can see them. But what is here important for us is that we can able to figure out, depending on the Avogadro's number, we can able to determine the number of molecules in 58 grams of water. Okay, by using the Avogadro's relation here. Excellent, very good. Anyone has any question before we move to the next slide?
Professor.
Yes, yes.
This is Marlene. I lost my connection last week on Friday. So where it says the increase in moving the decimal point,
Mm-hmm.
could you explain that?
Uh, what do you mean when you explain that? It's not clear. You
Um
mean the
where the math was
number of
19.3.
molecules?
Yes.
Yes, the number of molecules that can be increased. Yeah, the number of molecules that can be increased that we have, okay, we have 19.3 times 10 to the power of 23 molecules of water, right? When you multiply that. So the rule applies that when you move the decimal point to the left, instead of 23, you will have 24. You see,
Okay.
instead of 23, you will have 24. In other words, uh, let me clear up this a little bit. So for example, you may have 2.85 times 10 to the power of 2, right? This is just a number. This is like exponential notation. You have 2.85 times 10 to the power of 2. It's the same as 28.5 times 10 to the power of 1, or this is also the same as 0.285 times 10 to the power of 3. Now I want you to look the differences of the first one here with a different color, the second one here, and let me use a different color for the third one here. It's like A, it's like B, it's like C. It's a matter of what's happening here, that we're we are just moving the decimal point. The initial number was 2.85. Now instead of to get into this here, I move the decimal point to the right. When you move the decimal point to the right, the exponential number is decreasing, Marlene,
Oh,
decreasing. When you
okay.
move the decimal point to the left from the original number to the left, the exponential number is increasing. Okay,
Okay.
so that's how the difference is. Increasing or decreasing always comes to the fact that moving the decimal point to the right. Let me write this down so that moving the decimal point to the right, exponent is increasing. I mean, to the right, exponent is decreasing, sorry, is decreasing. If you move the decimal point, moving the decimal point to the left is vice versa.
Okay.
The exponent is increasing. Okay, takes this note, Marley. The exponent is increasing.
Okay.
Yeah, I'm going to send you this video anyway at the end, but that's the point. That's the point that when we are increasing or decreasing, depending on are you moving to the right, are you moving to the left? So earlier, Marlene was saying, I mean, Brittany was saying about 19.3 times 10 to the power of 23 versus 1.93 times 10 to the power of 24. These are the same. The only thing is that the original number was 19.3, but I moved the decimal point to the left. And guess what? The 23 becomes 24.
Okay. I
When you move
understand.
the decimal point to the left, here is the key. When you move the decimal point to the right, here is the key. You see?
Yes. Yes, sir. I got it. Thank
Okay,
you.
wonderful, wonderful. Is there any other question regarding with the counting the number of particles or molecules? This is the mathematical part, but it's also important. It's also useful to understand more. Uh, okay, so let me ask you this. I'm going to give you a practical question, and then this is going to be a practical question. I would like to calculate the number of moles in 185 grams of sodium phosphate. Okay, and calculate the number of particles. Calculate the number of particles. Calculate the number of particles in the same amount of sodium phosphate. Okay. Okay, let's do this as a practice, as a classwork. Yeah, I'll give you like a kind of 5 minutes and then we'll go from there.
So I got a question.
Yes, Brittany?
Is the PO4 a trick bag? Because that can come in like -3, 4, 5, and etc. So are we just keeping it plain, or are you trying to teach us a lesson?
No, there's no trick here. There's no any trick here.
Okay, I just wanted to make sure.
No, you have sodium, you have phosphorus, you have oxygen here. Depending on the number of atoms you can calculate. I'm pretty much sure you have a periodic table with you so you can find the weights of each. If you don't have a periodic table, unfortunately, that's a mistake. Okay, so you need to calculate that. So there's no trick here, Brittany.
Okay.
Would like to give out the answer.
Yeah, Professor, I want to try
Okay,
it.
go ahead. Who is that, Marcus?
Yeah.
Okay, go ahead, please.
All right, so the first thing we need to do is find out how many grams we have per mole of sodium. It's for sodium phosphate, right?
Sodium phosphate, that's right, that's correct.
Okay, sodium phosphate. So since we have 3 sodium atoms,
Mhm.
we look at our periodic table
Mhm.
and we see that the atomic mass of sodium is 22.990. So we have to multiply that 22.990 times 3. Then we have 1 phosphorus atom.
Phosphorus, yeah. Mhm.
Right, 1 phosphorus atom. So that's going to be 30.974.
Okay.
And we have 4 oxygen atoms.
Mhm.
So that's 15.999 times 4.
Mhm.
Okay, so the 3 sodium atoms is 68.97 combined.
Wait, for sodium, say one more time.
The 3 sodium atoms is 68.97, 3 times 22.990.
Okay.
Of course, the phosphorus is 30.974. And then our 4 oxygen atoms are 63.996.
Okay.
That adds up to 163.94.
163.94 AMU. Very
So
good.
that tells us that sodium phosphate has a molecular mass. Is that what that is?
Formula mass.
Formula mass, right?
Yeah,
Okay,
formula
so
mass.
sodium phosphate has a formula mass of
Yes.
163.94.
Why did we say this formula mass, Marcus? Can you explain that?
Because it's an ionic compound, right?
Yeah. We're talking about formula mass. The reason is that it's ionic. If it was molecular, if it's covalent compound, we'd have to say molecular mass. Yes, go ahead.
Got you. All right. So we know we have 185 grams, so we have to divide 185 by 163.94 to determine how many molecules we have. So that's going to give us what's that?
Okay, go ahead.
That'll give us 1.13. I'm using 3 significant figures since we have
1.2.
1.13.
Okay, that's some more.
Right.
Okay, I agree. Go ahead. Okay.
Okay, so that is how many moles we have in that 185 grams of sodium phosphate. And then to find out how many particles we have to multiply 1.13 times Avogadro's number.
Okay, I need more space here, so I'm going to take this 1.13 times 1.13 times
6.02
times 10 to the power of 23. We multiply that, that's right. Okay, so that gives us, go ahead.
Okay, one second. Let me put in my calculator real quick.
6.79.
6.79
times 10 to the 23rd.
Okay. Do you agree, Marcus, with Brittany's answer, or you have a different
Yeah,
one?
I agree. But it didn't take my thunder, but yeah, I agree.
Okay.
I mean, I did say nobody asked, Marcus. Like, no, I'm just playing.
Professor,
Yes, yes,
this is
yes.
Matt.
Um, um,
So,
okay, Matt. Hi, Matt. Go ahead.
so, so with the final answer, you always have to multiply with the Avogadro's number.
Yeah, now that's a good question. If you are asking the number of particles, how many particles? You see, that's the question. I removed it, but I was asking how many particles of sodium phosphate are there? How many molecules? When you have the question, how many? Okay, how many molecules? How many particles? Yes, it should be Avogadro's number. No question about it. Okay, so that's the nature of question. If you have how many molecules, how many particles, you have to convert that into Avogadro's number. Matt, does that make sense? Matt, are you there?
Yeah, I'm here.
Okay, is that make sense to you or?
Yeah, it does. But I didn't really catch the question. So,
Look,
question
okay,
about calculating the number of.
slide it, I gave you 185 grams of sodium phosphate. And out of that, I wanted to know how many particles or how many particles or molecules, how many particles of sodium phosphate are there. That's why we all are working with the Avogadro's number. The word how many is a key word here. How many particles, you see, of sodium phosphate are there? You see, Matt, that's how we have to move to the Avogadro's number. All right?
Right, Professor, I got you. Thank
Okay,
you.
all right, okay. If anybody has any question before I move to the next, okay, so we agree with 6.79, right, Marcus? With Brittany's answer, and anyone can also justify that?
Yes, sir. Totally agree with it.
Okay, all right, now 6.79 times 10 to the power, there are 6.79 times 10 to the power of 23 particles of sodium phosphate. Remember, this is a huge number. We also can write this in other formats, okay? We can say 67.9 times 10 to the power of 22 instead of 23. Why? I move the decimal point to the right. Previously, Marilyn was asking me this question. If you move the decimal point to the right, the exponential part will be decreased. So this is like in a multiple choice. If you see that, I want you to pay attention. So either 67.9 or 6.79 times 10 to the power of 23, they are the same. Okay, so that's how it is. So Avogadro's numbers are important to determine or to project the number of molecules or the number of particles in a given amount of substance, even though we can measure 185 grams. Okay, if I ask you measure 185 grams, I'm sure that you don't have any problem. You just have a scale or a balance, a top loading balance, or any regular scale. You can measure 185 grams of sodium phosphate. Now you change that into, that was one, yeah, 185. You change that into moles, and then by using the Avogadro's number, you can calculate the number of molecules of how many particles are there. Okay. So here uh, we are expanding the knowledge of the idea of moles. Each mole, each sample contains 1 mole of atoms. You have different substances here. You have 65.4 grams of zinc, 12.0 grams of carbon, 24.3 grams of magnesium, 63.5 grams of copper, 32.1 grams of sulfur, 28.1 grams of silicon, 207 grams of lead, 18.7 grams of tin. Now, they have different weights, as you see here. These are different masses, okay? They have different masses, but what do they have in common? they all have the same number of particles. In order to answer this question, you must have a periodic table next to you as we speak. I don't know where you are in the kitchen, or you are in the living room, you are in your sofa, wherever you are right now, you are in your desk. If you have a periodic table next to you, you can see the weight of zinc is 65.4 in the periodic table. The weight of carbon is 12.0 grams. The weight of magnesium is 24.3, etc., etc. So this is a 1 mole. All these are referring 1 mole. All these are referring 1 mole. So if they are referring 1 mole, all of them have 6.02 times 10 to the power of 23 atoms or particles. Okay, that's how the definition is. Okay, so you have 65.4 grams of zinc. There is 6.02 times 10 to the power of 23 atoms of zinc there, because that's 1 mole of zinc. You can verify that from the periodic table. Okay, so we can move to the next one. We're going to see about the molar mass. The molar mass, what's the molar mass? It's the mass in grams of 1 mole of a substance. The unit of molar mass is gram per mole. So if you change the AMU unit, okay, the AMU unit into gram per mole, then we're talking about the molar mass. So that's another terminology that we have to study here. That's called the molar mass. So the molar mass is the mass which is expressed in grams of 1 mole of a substance. So the molar mass of substance is numerically, please remember that, numerically is equivalent to the formula mass or the molecular mass. Previously, we were talking about the weight of aspirin. Aspirin has a molecular formula of C9H8O4, and the molecular mass of aspirin was 180.15. That's the molecular mass. When we bring this number, when we convert this number into gram per mole, now we're talking about molar mass. See, we just simply did 180.15 gram per mole. Okay, 180.15 mu versus 180.15 gram per mole. That's molar mass, and this one's molecular mass, okay? So if 1 mole of aspirin is placed in a balance in the lab, then we're talking about, it will read 180.15 grams. In 180.15 grams, there is 1 mole of aspirin. If there's 1 mole of aspirin, how many molecules of aspirin are there? Obviously, it's going to be 6.02 times 10 to the power of 23 molecules of aspirin. Okay, if you have double of that, if you have like twice of this amount, the number of molecules would be also twice, maybe like 12.06 times 10 to the power of 23 molecules of aspirin. That's how it goes. That's how we can able to track the number of molecules or the number of molecules of any substance by looking up of the molar mass or the number of moles. So like here, each sample here contains 6.022 times 10 to the power of 23 formula units of a compound or an element. You have different compounds. You have methanol, you have mercury iodide, you have octanol. So different molecules are here. So in the different molecules, the number of atoms is going to be 6.02 times 10 to the power of 23. So that's how we can able to determine the number of molecules. You can calculate the mass of each sample. That might be another thing. You can calculate the mass of each sample. If you want to calculate the mass of each sample, you can count the number of carbon, the number of hydrogen, the number of oxygen, again, the number of hydrogen multiplied by their respective weight in the periodic table. And then you can able to calculate their mass, their molar mass. The only thing, when you do the molar mass, remember that it has to be expressed in gram per mole. That's important, gram per mole. That's more practical, gram per mole. I was talking about the number of moles earlier. This is also an expression that how the number of moles will be the Avogadro's number here. Just for a comparison reason, the number of water molecules in the droplet of water, just one droplet of water shown below, is approximately 100 billion times greater than the population of the Earth. Now, nowadays, the population of the Earth roughly would be 7,442,000,000 people on Earth. One drop of water will have 100 billion times of this. 100 billion times of this one drop of water. Well, it's hard to explain it. It's very hard to explain it. So you can imagine how the number of molecules are very, 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 very huge, and hard to write writing with a number of significant figure. So that's why we have the mole is actually the key part. The mole is a great point to determine or to count the number of particles of the number of molecules. So this is also the same things that we discussed here. I think we have some more example we can able to do here. According to nutritional guidelines from the U.S. Department of Agriculture, the estimated average requirement for dietary potassium is 4.7 grams. That's a standard, is 4.7 grams. Now, based on this, what is the estimated average requirement of potassium in moles? Okay. If you have questions like this, I think the best experience is break the questions in two ways. Like on the left section, write what's given, okay, and what you know. On the right section, write what are you looking for, the want or the required value. What's that here required? And okay, and here what's the given value? Okay, so you have given that 4.7 grams of potassium. Potassium is K, and you know potassium is one of the alkali metals in group 1, and the molar mass of potassium is 39.10 gram per mole. Okay, this is given as well. So now they want you to calculate the average requirement of potassium in terms of moles, okay, in terms of moles. So you have to change grams. There's a plan here, there's a unit plan, there's a gram value has to be changed into mole value. So here is the conversion factor. 4.7 grams is given. You multiply that by 1 mole divided by 39.10. Always the unwanted unit has to be on the bottom. The desired unit has to be on the top. Okay, so you ended up with 0.12 moles of potassium. Okay, and also remember that we have applied significant figure. 4.7 has two significant figures, so that's why the answer has to be kept into two significant figure, which is 0.12. Okay, so this is a very great explanation. Example 3.3, which explain how to make convergence from grams to moles. Okay, if you ask it here, how many particles are there in 4.7 grams of potassium, then you can expand this by multiplying 0.12 times 6.02. I think that was a question earlier I was asked by Matt earlier. How do we know? Now in this case, the question, they didn't ask us to calculate how many particles of potassium are here. No, they didn't say that. They just say, what is the estimated average requirement of potassium in moles? You see, they stop here in moles. If they say that, how many particles of potassium are there? How many particles of potassium? If there is a word, how many? You see, Matt, if there's the word how many, then we would have to multiply 0.12 by 6.02. However, it was not asked, so they wanted to get the equivalent value in terms of moles. Okay, so let's move on with the next one. We have also Another example here. See, I want you to read carefully the word. The word is very important. Copper is commonly used to fabricate electrical wire. How many copper atoms? How many copper atoms in 5.00 grams of copper wire? You see now you have to be very careful. You have a keyword here. How many? So again, we're going to write the what's given. We have given the given mass, which is 5.00 grams of copper. We also have given the molar mass of copper. That's from the periodic table, 63.55 grams. We were looking for the atoms, not the moles, the atoms, particles of copper in 5.00 grams of copper. See? So the first thing that we need to do is we convert grams to moles, and then after moles, we convert that into atoms. So we have given a given value, that's gram, 5.00 grams. We multiply that by 1 mole divided by 63.55, and we get the mole value here, 0.07868 mole, and we multiply that by 6.022. So a lot of times you get confused with the 10 to the power of 23. Please don't worry about that. We just say 0.07868 times 6.022 times 10 to the power of 23. Multiply only these numbers, the coefficient numbers. Leave 10 to the power of 23 alone, okay? Don't get confused yourself with that. So that's how they came up with, when you multiply that, the calculator display will show you 4.74. I think there might be more significant figure, but we have to keep our answer to three significant figures, since we have given 3 significant figure here. So we get 4.74 times 10 to the power of 22, or I believe this might be 47 point, I'm sorry, this might be maybe 0.474 times 10 to the power of 23. I'm just guessing here, because if they have 4.7, you can multiply if you want to. I can use my phone here. If you multiply 0.07868 times 6.022. Yeah. So yes, actually, the calculator display shows you 0.4738, but yes, that can be rounded, times 4 times 10 to the power of 23. Now, this can be also written as 4.74 times 10 to the power of 22. So it's right. Okay, any question before we move to the next one? Okay, so so let's see here. So we have vitamin C, or ascorbic acid, is a compound with the molecular formula of C6H8O6. Okay, the recommended daily dietary allowance of the vitamin C for children aged 4 to 8 years is 1.42 times 10 to the power of -4 mole. What is the daily allowance in grams? Okay, again, we're going to write what's given here on the left side. We're going to write what's that we're looking for on the right side. So we have 1.42 times 10 to the power of -4 moles of vitamin C. We have we can, from the molecular formula, we can calculate the molar mass. We did that. Simply we multiply 6 by 12, 8 by 1, 6 by 15.99, and we get 176.124 gram per mole. So that means this is like 1 mole. All right. So once we have this, then the next step is we're going to change the grams. No, we're looking for grams. We're going to change the moles into grams. Okay. So mole is given. It's right here, 1.42 times 10 to the power of -4, and then we're looking for grams. So remember, when you do conversion factors, the secret is the given value has to be on the top, and the unwanted value will be on the bottom. So in this case, mole is the unwanted value, so it has to be canceled with mole. Okay, we're looking for grams. because here is the question will lead us to grams. So we get in 1.42 times 10 to the power of minus 4 mole, we have this much grams of vitamin C. Okay, I'm going to continue with the with this example, but as for Thursday, I want you to do this problem here. Wait a minute, this doesn't come up. Oh, here. This is a problem for everybody. A packet of artificial sweetener contains 40.0 milligram of saccharin with the formula. The molecular formula is given here. So based on this is a structural formula. This is a molecular formula. Based on this, you have 5 questions. What is the molar mass of saccharin? How many moles of saccharin are present? How many molecules of saccharin are present in the sample? How many moles of carbon atoms are there? And how many carbon atoms are present in the sample? So this is going to be an assignment for Thursday. And I wanted everyone to try this, and then we can continue from here, okay?